Today we're going to talk about 3 different types of how you get a charge, how you get charge electrically. Okay. So this one, charging by friction, this is the one that you're probably most familiar with. Think about time that you've been shocked or shocked something. Actually, if you've shocked something, you've been charged probably by friction. Okay. Whether that's like sliding down a slide or jumping on a trampoline or sliding your butt across the bleachers or sliding out of your car. Sometimes you get it with dribbling a basketball, a lot of different things. Shuffling your feet on the carpet, anything like that. So this is charging by friction. So when this happens is when materials with opposite electron affinities are rubbed together. That's a great question. I'll answer that momentarily. Okay. When materials with opposite electron affinities are rubbed together. Okay, electron affinity just means how much they want electrons. So here is a list, which you don't have to have memorized. Here's a list of electron affinity. So here, these type of materials are okay letting go of their electrons. So air, human body, glass, nylon, wool, lead, cotton, aluminum, paper, okay? And over here, so this is kind of more like organic materials, natural materials. And then down here, these are more man-made. So like Teflon, silicon, vinyl, polyurethane, polyethylene, urethane, polyester, polymers, stuff that's made in a test tube, in man-made, synthetic type stuff. Okay. So if you take something from this side and you take something from this side and you rub it together, electrons are being ripped off of both of materials just because of friction. Okay, but these materials would rather have electrons, those loose, freed electrons, and these would be okay letting them go. So these become negatively charged, and these materials become positively charged. You good with that? And so next time you shock somebody or something, think, wonder what just happened to make that happen. Okay, charging by friction. So if you have a conductor and you charge it by friction or you give it a charge, whatever, however you do that, the charge is just a factoid. The charge on a conductor is always going to be on the outside. Outer surface is going to be spread out. Okay? So the charge on a conductor will always be on the outer surface and spread out around the entire surface. Good with that? Factoid. Conductor spreads out, always on the outside. Versus an insulator, so it would be choice C. Versus an insulator was charged by friction. It's going to experience just where it was rubbed, and it's going to be isolated. Okay. that make sense in terms of the characteristics of conductors and insulators? Conductor, the charge will spread out always to the outside, not in the middle, not in the interior, but only on the outside, versus insulator, it's only going to be charged where it was rubbed. Okay. All right. Second way is charging by conduction. This is when a charged object touches neutral object. Causing the neutral object causing the neutral object to have same charge as the initial charged object. Oh my. When a charged object touches a neutral object, causing the neutral object to have the same charge as the initial charged object. A lot of charges in there. Okay, good with that. So, what does that look like? So let's say we start with a neutral piece of metal. Okay. A neutral piece of metal, and then we bring in a negatively charged object. So not an electron, but like a bowling ball that's negatively charged. Inside the conductor, the electrons respond. They're repelled to the far side of the conductor. Good with that? So far, we have not charged by conduction. This is just, we've just caused it to polarize. Okay, this piece of metal is still neutral because you have the same number of electrons as protons. Okay. Now, when you bring this when you bring this to the point where it touches, the touching allows for a bridge or a road for electrons to transfer. Okay. And here's what governs the transferring. Electrons are always going to go to a better environment. Okay, they will never be satisfied. Even if it's a 1-to-1 ratio, if they can find a place where there's more exposed protons, that's where they're going to be. They'll always go to a greener field. Okay, so if you were an electron, where would you rather be? In this negatively charged bowling ball, or over here where you have a lot of exposed protons? Exposed protons, like, man, look at, oh man, it's so crowded in here. This looks so much better. And so electrons go out of the negatively charged object into the once neutral, making this what? Charge on the conductor is now negative. Good with that? Charging by conduction. Yep. Try that one out. We got a neutral object and bring a positively charged object near. Charge it by conduction. Tell your neighbor what you think. Correct answer is, guesses are C. C is correct. Good job. So, inside here, the electrons are like, ooh, look at the positive polarizes. Okay? And then when the positive object is touching this, electrons are like, man, whoa, woo! And so they jump off, leaving the once neutral object now positively charged. C is correct. Okay. Good with that? Okay. Before we talk about the third way, we need to introduce this term called ground. Okay, you might have heard of being grounded electrically, not like you're getting punished, but like you have a ground wire, a ground strip, or something that's grounded. Okay, so it's this idea. Ground is anything huge and neutral. The wiring in your house, the ground wire, the third prong, electrically is connected at some point to your plumbing, to the pipes in your house, which that electrically is connected to the dirt somewhere. That's where the term ground comes from, because you're actually putting it into the ground. Okay, but in a more general case, ground is anything huge and neutral. Okay, it's kind of like this idea that if you take a bucket of water and you dump it into the ocean, you really didn't raise the sea level. It's still the same, even though you added some water to the ocean. Okay, so if we pump electricity into the ground's still neutral just because it's so overwhelmingly big and there's so many more electrons and protons. In lab today, you are going to be ground compared to the object that we're looking at, because you're going to be huge and neutral in comparison. Okay, so it's always a 1-to-1 ratio of protons to electrons. Okay. Third way is charging by induction. I'm going to take you through this process first before I try to write it down. Here's ground again. Is that what you need? Okay, here's induction. It's a process. So the first step is we have a neutral object, and then we bring a positively charged object near. Not touching, but near. So think about what happens, visualize what happens what goes on with protons and electrons inside this thing because it's in the presence of the positively charged object. Thumbs up when you have a guess. What happens inside of here because of this guy? I just want to just looking for a thumbs up, see if there's a pulse out there. Yeah, we got a lot of dead. Like, awesome. Okay. Protons just distributed throughout. Okay, but electrons, they're like, whoa, look at those protons. Okay, so it polarizes. Good with that? We have not charged it yet. This is still neutrally charged. It's just polarized. You guys still have the same number of electrons as protons. Then we connect the opposite side to ground. Okay, so what that's doing is pretending we're connecting this to something huge and neutral, like the Earth or something, that has an equal number of protons and electrons. Now remember that protons and electrons, that electrons will always go to a location, a scenario, a situation that has a better proton to electron ratio. So if you were an electron, where would you rather be? Would you rather be here in a 1-to-1 ratio in the ground, or would you be rather up here with all these exposed protons? You're like, whoa, look at all these exposed protons. This is, oh man. And so in this scenario, electrons are going to come up from ground because we made this connected bridge or road into here. And they're like, yeah, hey, how you doing? Hey. Good with that? Okay. And then we take the connection with ground away, stranding these electrons. We marooned them. Okay. And then the final step is we take this positively charged object away. And so now these electrons are like, oh man, I guess I'll go back home. And they come back like, whoa, who invited? Why did you? Oh, and now this is charged what? Negatively charged. Charging by induction. Okay, so it's that whole process. So if I could put it into words, it would, I mean, you're welcome to put that in your own words, but it's when a charged object polarizes a neutral object. You grimacing at. I'm not going to say what I want. Be nice. Okay. You know what it is? No. Real icy outside. Do what? It's real icy outside. Yeah. So you know what I want to say to your class. I do. I do. I'm just going to throw this out at you. If Mr. Powell ever comes in and says something, be very very, what's the opposite of gullible? Be very critical, very like don't be gullible. Think about it real carefully before you start. Okay, when a charged object polarizes a neutral object, and then grounding, and then connecting, that's a C, connecting, polarized, object to ground, allowing electrons transfer, leaving or causing the object to have the opposite charge as the initial charged object. Whew. I don't know. Definitely not the most condensed way to say that, but if you can come up with something better, you can go with it. When a charged object polarizes a neutral object, then connecting the polarized object to ground, allowing electrons to transfer, causing the object to have the opposite charge as the initial charged object. Pretty sure that's like 3 run-on sentences combined. I mean, you can summarize that however you want to. It's that process I just took you through. Yep. There you are. All right, charging by induction. And now we're going to do a lab.